Okay, so what we want to say is I'll cut this short for the intercept talk because the slope is really the more interesting thing. But the USGS asserts, as I said, that any of the TiO2 production numbers already reported include the nano. So what we did, and this is the best case we could do at the time, was we used out of the 5 or 6 companies that are producing nano TiO2 right now, we used the most transparent production process and looked at their maximum capacity and said if they operated at this maximum capacity for 365 days a year, every day, the very most, because we want an upper bound, then how much would be produced? And if we multiplied that by all of the companies out there, then how much is that? And it turns out that that's about 1,700 metric tons per year, which ends up being less than 0.5% of the global production. Now that's a pretty iffy estimation because it's based on their patents and what they're saying they can do, but it gives us a starting point. And there's a lot of caveats there, including the fact that DuPont has a patent and they also participate in nano titanium dioxide production. So it's quite possible that they could jump this up by, and that one of these 5 companies changing the method by which they produce it could change the entire industry. Because that is incidentally what we saw DuPont do in the 80s with the chloride process. So, so that's all subject to a lot of change, but just showing you the methods how we got it. So that's basically our intercept. That's supposed to be a check mark, so you're not missing much with that little MAC conversion problem. So for our upper bound estimation, we say that in 2003, which is the beginning of that Altair Nano patent, we're at about 2,000 metric tons a year in nano production. So then we're going to move on to trying to understand some market forces a little bit and then apply the biotech conversion method to see how much could we see at the most in the environment. So just a little of the current demand profile for titanium dioxide. Almost all of it that is mined is turned, the titanium ore is turned into titanium dioxide because as an ore, as a steel replacement, it's just not very economical to use titanium for anything in that industry. So it all goes to titanium dioxide, and that looks like it's going to stay the same. And as you can see, most of it becomes paint and lacquers and varnishes. Some becomes paper, some becomes plastics, and a very small percent becomes other things, which includes almost all of the first things that are going to be attractive for the nano uses. So catalysts, cosmetics, all kinds of other things, like including glass. Self-cleaning glass has titanium dioxide in it. So it's important to notice that most of the original things, the high margin applications, are only make up right now a small percentage of what titanium dioxide is used for. But it is useful for some of these other things. Okay, this is just the growth over time. It's a pretty steady growing industry. It's mostly stayed the same. Paper has stayed, or paints, I'm sorry, have stayed about half of it for most of the industry's life for the, since, well, I guess I have it since 1975, but the data looks very similar. It wasn't as pretty of a graph if you go back. But, okay, so the improvements at the nanoscale are universal across all of these applications, but they're incremental rather than revolutionary, which is an interesting observation. So for something that's white, it makes it whiter because it's got a better refractive index. And for something that's photocatalytic, the fact that it's nanoscale and it has more surface reactivity makes it more photocatalytic. But it's mostly doing things that it could have done in the bulk. It's just doing it better. So that's one thing to note. So these, all of these top 3 and some of the other portion use the refractive index quality, which means all of the, the paper, the paint, the plastics, like its opacity and its whiteness. And that is improved at the nanoscale. The photoactivity is mostly used in the plastics and in all of these other applications. So that's something to notice too. So prices. Right now, basically when you take the titanium ore and turn it into titanium dioxide in the bulk form, you increase its value by an order of magnitude. To make it go to nano, you almost increase it by 2 more orders of magnitude. So this is making it so those small 3%, of applications, the catalysts and the cosmetics and things, are carrying a lot of value. So that if someone, this could go a couple different ways. If someone is producing it and it's a demand-based price, it's based on what the market will bear right now because it's hard to get this. They probably want it to stay at $90 per pound. But at the same time, that's going to probably cause more people to want to be able to produce this $90 per pound product. So given the fact that we have this very centralized industry with a few producers and a few methods, it would maybe make sense for some people to update to a way that they can produce something that if it's going to be just as good for all of the other applications, maybe they can get in on this, this increased value part of it. That won't stay the same, obviously, right now. Once it becomes a commodity, it's much different, but it was interesting to me. So this is the only thing that is important about this is that all of the U.S. capacity is produced by 4 producers at only 8 locations. So that's just another kind of check in the column of that this could be a mobile industry pretty rapidly. If they did change, it would not take a huge domino effect before you saw multiple changes. So what we say, now we have the intercept, which is that we start out with very little nano titanium dioxide, and the far upper bound, how much could it be? We could say, as a conservative estimate, you could say it could all completely go to nano, right? So there's almost a universal improvement of performance. So all the market sectors benefit, but obviously the high photoreactivity is going first. High margin applications exist across product sectors, which may help pull it. The small number of producers, as I said, and also the aging sulfate technology. All of those point to the absolute upper bound of full transition. So now the interesting part is, how do we get this rate? So what we did was to search for titanium dioxide patents and articles throughout the U.S. This is for U.S. I think I said that, but I want to make that clear. So we did a probabilistic search, and at this point I'm talking about the UCLA Economics and Sociology Department collaboration. And so right now I'm presenting work that I helped on, but am not the primary person. So I'm a little bit out of my expertise area. But so we used these search terms and looked at all the patents in the patent office, and then all of the different research articles across multiple search engines. And we also looked in Nanobank, which is a nano database that's also run out of UCLA. I'm sure everybody may have heard of that, but and looked at the share of nano within those overall titanium dioxide. So, and I apologize on this, I couldn't get the original graphs, so I couldn't change the colors for you, but I think we can get through it. So this is to sort of make the case why nanotech is like biotech, besides describing that characteristics that I did where they're both revolutionary industries. They both are looking at a pretty innovation-driven field and not based on things that techniques that have been used before to make the same end product. So this is just, I'll show you that. The top line is nano articles, and I think I can use this. So this is nano articles, and this is nano patents. So this is starting from the different years. So for biotech, it's starting from 73. And for nanotech, it's starting from the late 80s, around the time of the discovery of the fullerene in 85. So just to set them back to the same starting period, the articles are growing a little bit more steadily than the bio articles were, but about kind of with a similar trend, just a different magnitude. And then the nano patents growing like this, whereas the bio patents hit a jump right here and then jumped up. So there, the sociology department felt like this was close enough of a match to